In today's hyper-competitive world, people are obsessed with success. For decades, researchers and scientists have studied the issue of success and quantifying them. However, not all success can be easily quantified, such as the success of researchers or artists. Unlike sports, where there are many objective criteria used to measure success. This project exploits network science techniques to understand and predict success of data scientists. We utilize database systems and logic programming (DBLP) datasets to track the career of data scientists in data management conferences over time and perform network analytics to understand and quantify their career success. Data scientists from 13 data management conferences are used to create a co-authorship network to find relationships and correlations. We will now move on to the analysis demonstration. This is the application that will help us analyze the DBLP dataset. The first step will be extraction of data and have to be done first before doing any of the subsequent analysis. Users first input the conference's venue and label their tier. Users can also do this by uploading a text file. Based on the inputs, the program will then extract the relevant data from the DBLP dataset. The extracted information will then be used for the rest of the analysis. There will be two extracted data, an author's list of publication including the venue as well as the year of publication and author's co-author list. We will now move on to the second section of this application, distribution of number of publications. We can check the distribution of number of publications for Tier 1 authors, non-Tier 1 authors as well as authors from each of the venue selected. To begin the analysis, users first check the options that they want to analysis and then click Analysis. The analysis will begin and when it's done, it will display the selected options. As we can see, the distribution follows the power law, indicating that only a small percentage of authors reside at the top of the bulk, monopolizing the number of publications. Next, we can analyze the movement between conferences by constructing a network graph. Users will be able to select the analysis they want to do. Users can select the tau value for the network graph. Similarly, users choose the options they want by checking the options and then click Analysis. The analysis will begin and when it's done, it will display the selected options. This figure shows the network graph between the conferences. Nodes represent conferences. Weighted directed links between nodes represents the number of authors that first published in Conference I and then in Conference J for the first time. Different colors represents the different tiers. Through this network, we can see how long an author took to publish a publication in a higher tier conference than their previous publication. Over 80% of the authors publish in a Tier 1 conference within 8 years after their previous. A similar pattern can be seen for Tier 2 conferences. Next, we can analyze whether initial score affects the reputation of data scientists. Initial reputation are calculated using the first 5 years of an author and as such, this analysis is only applicable to authors who have a career length of at least 5 years. Users can then select the cutoff point between the top authors and the rest of them. Once the user has selected the options they want, the analysis will begin. We can see that majority of scientists started with a low initial score of less than 0.4. Authors who started with a low initial score have much lower career score compared to authors who started with a high initial score. Through this, we can see that there's a positive correlation between initial score and career score. Lastly, this application allows us to analyze the collaboration between scientists. Authors that have no co-authorships with other authors will not have any links and will not appear in any of the network graphs. After selecting the options, the analysis will begin. This is the co-authorship network among authors. Nodes represent an author. Degree of nodes represents the number of co-authorships an author. Weighted undirected links between nodes represent co-authorship between two authors. Width of the links represents the number of co-authorships between the two authors. We can see that there is a central community and any of the nodes that are not part of it have very little edges. These nodes are also much smaller compared to the nodes found on the central community and these authors have very little publications, indicating limited success. We will now present the key findings of this project. Reputation and success of data scientist is quantifiable using one's publication. Initial reputation plays a huge role in defining a scientist's success. If scientists do not break through within 8 years, they are unlikely to break through. Scientists who do not collaborate are stuck with limited success. We have come to the end of the video. Thank you for watching.